These are the counter levers. They count the number of balls that have gone on them and use that to tell the time. So the bottom counter is the number of minutes that have passed by, which in this case is 6 minutes, and then this is the number of seconds that have passed by, which in this case is 28 seconds. So therefore the time on the clock right now is 6 minutes and 28 seconds. However, there's one more thing that I must mention. Specifically, the time readout on the counters isn't always the official time according to the clock. To explain why, I first must explain how to start the clock. So I already showed you one way, which is to release a ball on the tracks here. However, that's not the most accurate way to start the clock. A more accurate way will be to place the ball on top of the primary escapement so that there are now 2 balls on top. And even though this isn't the most accurate way to start the clock, it's pretty good for our purposes right now. So to start it, I simply have to push the primary escapement. And then once the ball has reached this point over here, 4 seconds have passed by, right? Well, the counters still display 0 minutes and 0 seconds, so that can't be quite right. Therefore, if the ball is at the base of the primary escapement or anywhere along this track here, then I need to add 4 seconds to whatever the counter says. So here it will be 0 minutes, 0 seconds, plus 4 seconds, and therefore the official time of the clock would be 4 seconds. Let's see this in action, so I'll go ahead and start the clock now. Alright, so let's see what time the clock reads right now. It will just be 3 minutes, 56 seconds, and then since there's a ball on this section of track here, it'll be plus another 4 seconds, so it'll be 4 minutes. So the clock right now reads 4 minutes of time. Anyways, here's what happens when 4 minutes have passed by. And here's what happens after 15 minutes. You can probably already tell what's going on, but just for fun, here's a slow-mo clip with the ball covered in black Sharpie. It's fair to say that these counter levers were the most calculation-intense portions of the clock. The reason for this was because they had very specific requirements, and I had to basically find the optimal design for satisfying those requirements. The first one was, if there's just one ball here, I can't have the lever just tip over like this because then I'll be too early. The second requirement was, if there are 14 balls here, which is one less than the number required to tip it over, I can't have these 14 balls tip over the lever either. Final requirement is, once there are 15 balls, it has to tip over, like so. I won't bore you with the details of the calculations, but I do want to share some of the things I learned through them. Specifically, I realized that I should try to keep the mass of the lever relatively low, and I should also try to shift the center of mass to the right as far as possible. So it's hard to see, and it's hard to see this entire lever, but I made a copy, so it's okay. So you can see that on the right side I have a counterweight, which is just meant to help, focus that in, which is just meant to help shift the center of mass to the right. And even though this ended up increasing the mass of the overall lever, it was okay because shifting the center of mass to the right with this counterweight was a lot more important. If you think about it, these counter levers actually involve both 3D printing and 2D printing, because the green part, the plastic, is obviously 3D printed, but then the labels here, they're basically just strips of paper with the numbers printed on them with the traditional inkjet printer, which is basically 2D printing, right? So the reason for this is because the numbers here are extremely small. There wasn't much space to write them out or print them out, so I figured out the only option was to use an inkjet printer. Now for something like the plaque, which you saw in the timekeeping section, you can see that the letters are a lot bigger, so it was actually possible to 3D print that. But for tiny numbers like this, it's really not possible to 3D print it, at least not with the 3D printer that I have. Anyways, what I did was I printed out the counters up until around here, at which point I manually paused the print and I inserted the labels into the counters. And I secured the labels using some rubber cement just to make sure they wouldn't blow away or something once I resumed the print. So once I got the labels in place, I simply resumed the print and I finished it up. Oh, and another thing. So when I was building all of this, I kept dropping balls and having to pick them up, which was really annoying. So I started using a magnet to pick things up. Well, that was actually a pretty bad idea because I ended up magnetizing some of these balls. And they're not magnetized anymore, but whenever, or sometimes when the counter tipped, some of the balls just wouldn't roll down because they were all stuck together, and it's a lot harder to slide than this to roll. So they would just stay here and not roll down with the rest of the balls. So yeah, I just wanted to point out that these balls should not be magnetized because that can cause problems. Anyways, there's an issue with these counters because every time 1 minute passes by, it sends a massive group of balls down all at once. And this is an issue because in a section below it, the collector isn't able to process these balls all at once because it would create jamming or just balls exiting the clock when they're not supposed to, and in general it would just cause it to malfunction. So that's why I have this blue lever here, which is called the regulator because it helps regulate the flow of the balls through the section. So I'll go ahead and demonstrate now. And it's easy to see that it splits this group of balls up into something that's actually manageable for the collector. Here's a slow motion of the regulator in action. I previously experimented with the wheel design, but even if I had gotten the prototype to work, the balls would have passed through it way too fast. Fortunately, in the current regulator design, that's not an issue because when I run it, each ball has to make it around this point before the next one comes in, so there's plenty of time between each ball, and it's pretty easy for the collector to handle that. I wanted to maximize the time between each ball, so I shifted the axle of the lever as far to the left as possible. However, even though this increased the time between each ball, which was good, it ended up requiring me to add counterweights over here because I need the lever to always be in this up position, or at least to naturally be in this up position. This is because when a ball comes in, like so, I needed to slide in over here so that it can automatically just drop down and keep going. If, however, the lever was naturally in a down position, when this ball comes in, it would just be stuck against that piece of plastic there, and without this, it wouldn't be able to go through the regulator. So there you go, that's the display section. And I just wanted to point out something I noticed. So the counters take in individual balls, like so, and then once it becomes full, it sends them out as just one giant group of balls. But in contrast, this regulator takes in that giant group of balls and splits it back into individual balls. So one of the interesting things I noticed about this display section as a whole is just the fact that the regulator and the counters are basically complements to each other, performing the opposite tasks but allowing the clock to function because of that.